Our planet is a restless soul, its surface a mosaic of ever-shifting plates. These plates, colossal slabs of rock, glide across the Earth's mantle, creating mountains, volcanoes, and earthquakes. Among them, the Indian Plate stands out. This massive plate, once a solitary traveler in the vast southern ocean, embarked on a journey northward millions of years ago. Its collision with the Eurasian Plate gave birth to the Himalayas, the highest mountain range on Earth. This tectonic clash, a slow-motion collision of titans, continues to this day, shaping the landscape and influencing the lives of billions. But beneath this dramatic surface spectacle, a hidden geological drama is unfolding, a process far stranger than the familiar dance of plate tectonics. The Earth's crust, the outermost layer we call home, is not a single, solid shell. It's more like a complex layered skin. Beneath the continents, this crust is thicker, forming what geologists call the continental lithosphere. This lithosphere isn't just crust, it includes the uppermost part of the mantle, a layer of hot, viscous rock. Now imagine this. What if this lithosphere could peel apart like layers of an onion? That's essentially what's happening beneath the Himalayas, a process called delamination. In this case, the Indian Plate's lithosphere is splitting. The upper layer is pushing upwards, contributing to the towering heights of the Himalayas. But the lower layer is doing something unexpected. It's sinking, plunging down into the Earth's mantle. Delamination is a hidden process, occurring deep beneath the Earth's surface. This phenomenon involves the peeling away or separation of the lower part of the Earth's lithosphere, which then sinks into the mantle. It's a process that can have profound effects on the surface, including the formation of mountain ranges and volcanic activity. So how do we even know it's happening? Given that it occurs so far below our feet, direct observation is impossible. Instead, scientists rely on indirect evidence and advanced technology to uncover the secrets of the Earth's interior. Scientists have developed ingenious methods to peer into the Earth's interior. These methods include the use of seismic waves, which travel through the Earth during earthquakes, and the analysis of gases released from deep within the planet. One clue comes from an unlikely source: hot springs in Tibet. These hot springs are not just picturesque natural features, they are windows into the deep Earth, releasing gases that have traveled from far below the surface. These springs release gases from deep within the Earth, including helium. Helium is a noble gas, and its isotopic composition can tell us a lot about its origin. By analyzing the isotopic composition of this helium, scientists discovered something remarkable. The specific ratios of helium isotopes provided a fingerprint that could be traced back to the Earth's mantle. The helium had a signature that could only have come from the Earth's mantle, far below the crust. This was a significant finding because it indicated that material from the mantle was making its way to the surface. This suggested that material from the mantle was rising up, a telltale sign of delamination. Delamination can cause the overlying crust to become more buoyant, leading to uplift and the formation of mountain ranges. Another powerful tool for studying Earth's interior is seismology. Seismologists use seismic waves generated by earthquakes to probe the structure of the Earth. Just as X-rays allow us to see inside the human body, seismic waves from earthquakes allow us to image the Earth's internal structure. These waves travel at different speeds through different types of rock, providing a detailed picture of what lies beneath the surface. By analyzing how these waves travel through the Earth, scientists can create three-dimensional images of the Earth's interior. These images help us understand the composition and behavior of the Earth's layers. These images, called S-wave receiver functions, revealed a distinct gap beneath the Himalayas. This gap was a crucial piece of evidence in understanding the process of delamination in this region. This gap, a zone where seismic waves traveled differently, corresponded to the sinking lower layer of the Indian Plate. The sinking of this plate is a key driver of the tectonic activity that has shaped the Himalayas over millions of years. Section 4. A two-tiered descent, uplift and sinking. This section delves into the fascinating interplay between geological forces that shape our planet. The Indian Plate's delamination is a geological balancing act, a story of simultaneous uplift and sinking. This process is crucial in understanding the dynamic nature of Earth's crust. As the lower, denser layer of the Indian Plate sinks into the mantle, it exerts a downward pull. This sinking action is not just a simple descent but a complex interaction with the surrounding mantle. This pull, in a surprising twist, contributes to the uplift of the Himalayas. The majestic peaks we see today are a direct result of this intricate geological dance. Imagine a seesaw, with the sinking layer on one side and the Himalayas on the other. This seesaw effect helps us visualize the balance of forces at play. But the story doesn't end there. The ongoing processes beneath the Earth's surface continue to shape the landscape in ways we are still discovering. The sinking layer, now detached from the plate above, continues its descent into the Earth's mantle. This descent is a slow and steady journey, influencing geological activity over vast timescales. This process, called lithospheric dripping, is like a slow-motion geological drip. It's a phenomenon that occurs over millions of years, gradually altering the structure of the Earth's interior. The sinking material, denser than the surrounding mantle, can create upwellings of hot mantle material. These upwellings are crucial in driving volcanic activity and reshaping the Earth's surface. These upwellings can, in turn, influence volcanic activity, and even the movement of continents over millions of years. The interconnectedness of these processes highlights the complexity and beauty of Earth's geological systems. Section 5. The Himalayas, a mountain range forged in plate tectonic fire. The Himalayas, a testament to the power of plate tectonics, are often described as young mountains. Their towering peaks, sculpted by erosion, still bear the scars of their violent birth. Delamination adds a fascinating wrinkle to their story. While the initial collision of the Indian and Eurasian plates set the stage for their formation, delamination is now playing a key role in their continued growth. The sinking of the lower lithosphere provides the upward force needed to keep the Himalayas rising, even as erosion relentlessly wears them down. This process also explains why the Himalayas are still geologically active, with frequent earthquakes and ongoing mountain building. Delamination, it seems, is the hidden engine driving the Himalayas' continued ascent. Section 6. Tremors in the Earth, Delamination and Seismic Risks. In this section, we delve into the intricate relationship between geological processes and seismic activities. The Earth's crust is in a constant state of flux, a dynamic system driven by the slow but relentless movement of tectonic plates. These plates, massive slabs of rock, float atop the semi-fluid asthenosphere, shifting and colliding over geological timescales. Delamination, with its interplay of uplift and sinking, adds another layer of complexity to this system. This process involves the peeling away of the lower crust and upper mantle, which can lead to significant geological changes, including the formation of mountain ranges and basins. As the lower layer of the Indian plate sinks, it creates stress along the boundary between the plates. This subduction process is a key driver of seismic activity, particularly in regions where tectonic plates converge. This stress can build up over time, eventually releasing in the form of earthquakes. These seismic events can vary in magnitude, from minor tremors that are barely felt to devastating quakes that can cause widespread destruction. The Himalayas and surrounding regions are already among the most seismically active areas on Earth. The collision between the Indian plate and the Eurasian plate has created a complex network of faults and fractures, making this region particularly susceptible to seismic activity. Delamination could potentially exacerbate this risk, making the region even more prone to powerful earthquakes. The peeling away of the lower crust can lead to additional stress accumulation, which may trigger more frequent and intense seismic events. Understanding this process is crucial for assessing seismic hazards and mitigating the risks to the millions of people living in the shadow of the Himalayas. Researchers are continuously studying these geological processes to develop better predictive models and improve earthquake preparedness in these vulnerable regions. Community drills and education programs are essential in helping residents prepare for potential seismic events, ultimately saving lives and reducing the impact of these natural disasters. Section 7. A new perspective on our planet. The discovery of delamination beneath the Himalayas is a reminder that our planet is full of surprises. It challenges our understanding of how Earth's systems work and highlights the interconnectedness of geological processes. What happens deep within the Earth's interior can have profound effects on the surface, shaping landscapes, influencing seismic activity, and even affecting the course of human history. The Himalayas, once seen as a textbook example of plate tectonics, now offer a glimpse into a more complex and nuanced geological reality. By studying these processes, we gain a deeper appreciation for the dynamic nature of our planet and the forces that have shaped it over billions of years.